So using high-frequency ultrasound for sizing ICLs. Let's look at the evolution of the way that we think about sizing. So the ICL, as you know, has been available for refractive surgery as a phakic IOL since the 90s. And I have very close friends who were doing high volumes of these ICLs in the 1990s. One of them close to me in Europe, Christian de Courtin in Switzerland, Carlo Lovisolo in Milan, and of course Roberto Saldivar, who's put in 26,000. How was this done? Well, the assumption was made that the white-to-white was going to be good enough. And that really was version 1, and it worked pretty well. Over time, it was realized that it was possible to add, in a multivariate regression analysis, that it was possible to add other factors, such as refraction, keratometry, and the AC depth, that these would refine the selection of the ICL, in addition to white-to-white. And I call that version 1.5. Now, I looked at the correlations between all of the measurements we could make that weren't ultrasound and the actual measurement of the sulcus with ultrasound. And we published a very nice paper, which I won't go through all the details here, but we showed that no matter what you do with external measurements, you're still going to be quite unlikely to be able to predict the diameter of the sulcus within 0.5 millimeter. That's the best you could do is about 25% of the eyes will still end up with more than 0.5 millimeter error in terms of predicting the sulcus, using all kinds of external measurements. Carlo Lovisolo was an Italian ophthalmologist in Milan who was an early adopter of ICLs and wrote the first textbook. It came out in 1999. It was about 250 pages. It's a beautiful piece of work. And he was adamant that sulcus measurements was the way to go because of the sizing surprises that we occasionally would get from using white-to-white sizing. And others, of course, started to study these things and produce their own formulas based on sulcus to sulcus. And there is a subset of ICL surgeons who use ultrasound and won't do the sizing from white-to-white. They'll do it from their sulcus measurements. So when you look at the review studies that were done on the validity of using ultrasound versus white-to-white just like that, it was so mixed up that it looked like there was no benefit to using ultrasound. However, Doherty in LA was part of the US FDA ICL study, and he published a paper with a table to look up, based on the sulcus to sulcus, what ICL you should put in, including the ICL power, because as you know, the power of the lens changes the dimensions of the back surface of the ICL, right? The higher the power, the thinner the ICL in the middle, so the further away it will be from the crystalline lens. I would call that version 2.0, is using the sulcus to determine the ICL size. Now, Kojima in Japan said, well, true, but that distance from the surface of the crystalline lens to the back surface of the ICL will also be determined by how high the crystalline lens surface is. And so he said, let's add sulcus to sulcus lens rise. So the lens rise from the sulcus to sulcus plane, and he found it to be a useful, statistically useful parameter to increase the accuracy of the ICL prediction. So I would call that sizing formula 2.5. And I was using the Kojima formula myself, but using much higher frequency ultrasound, and I was expecting better results. So we looked at a series of 42 eyes that we had scanned, and the idea was to do a multivariate regression model, and we looked at many, many variables. So we were looking at all the normal things that you could measure, but then within the ultrasound images, we thought about looking at AC depth, the actual angle to angle, the sulcus to sulcus, of course, the sulcus to sulcus lens rise, the zonule to zonule measurement, which is where the anterior zonule inserts here, the zonule to zonule lens rise, because we thought, well, the sulcus lens rise might not be as good as the zonular lens rise, okay, and then this the distance between what we could see as the inner ciliary body diameter. And what we found was that the inner ciliary body diameter was such a powerful predictor of ICL sizing that it threw the sulcus to sulcus out. We couldn't get it back in. It wouldn't go into the equation. So it substituted for it. It was that hard a number. And of course, the sulcus to sulcus lens rise remained. So, very humbly, we've now called this version 3.0. I mean, it's our nomenclature, so we're allowed to use it. We call this 3.0. We wouldn't go back to 2.5 because we know how much better this is now. So the other thing that I noticed was that we were always given a recommended lens size, right? The Ocos website gives you a recommended lens size. The Doherty gives you the recommended lens size. The Kojima gives you an equation. And I was thinking, no, what we really want is we want to know what the sulcus will be for all four sizes and then decide which one to put in. Because obviously, if you have a younger patient with a very deep chamber and knowing what the changes are going to take place over time, you're going to want to get further up than 500, let's say in a 22-year-old minus 12, with a 3.2 anterior chamber, that crystalline lens is going to grow over the next 20 years. You don't want to have to take the ICL out. So you want to maybe start at 600 or 700 rather than start at 400. Whereas if you have a 43-year-old minus 12 with a 3.0 chamber, maybe you want to go more 500, 400 than 600, 700. So you want to be able to choose the lens. And so we thought of producing the formula and making it so that we give the predictive volt for whatever size. There's only four, so you predict which one you're going to choose. So the results that we got once we got our formula were as follows. So this is 42 eyes, and we had a mean of 500 microns, which is kind of what we expected. And we had a range of 710 microns. With the STAR formula, had we used the Ocos website recommendation only, we would have got a higher mean. We all know that, right? That many surgeons will automatically go one size lower in certain circumstances. With a similar range, the Doherty and Kojima, again, similar range, about 700 microns range from the lowest to the highest. Now, when we looked at all of these equations in the eyes that we did, we found, for example, that the Ocos website recommended a lens size that was 2 sizes larger in a quarter of the cases. So again, this all fits with the fact that we know that the Ocos website often recommends a lens that's maybe a little bit too big. What is the optimal volt? Well, we used to think of it as it should be 500. And if we think of it that way, this predicted volt, if we were to just theoretically plug, this is very unmathematically kosher, but if you take the eyes that we did and look at the formula that was derived from those eyes, and then go back and see, would I have used the same lens or would I have used a different lens? And if I had used a different lens, what's the lens separation that I would have got? So we predicted that we would get a greatly reduced scatter from top to bottom. And we predicted that we would get about a half of the interquartile range. The other thing that I thought was interesting was to consider what the histogram of the lenses that we had chosen. And what I noticed was that it wasn't normally distributed. In other words, there was a skew distribution in our selection of lenses. Where's the mean of this graph? It's about there. So let's say that there was a mean lens. Let's just put it exactly between 12.6 and 13.2, just for argument's sake. If there had been a 12.9 available, how often would we have chosen it using our 3.0 formula? And the answer is a third of the time. Now, if we had that 12.9 available, what would have that done to the interquartile distance? It would have made it 2/3 of the previous and a quarter of the distance of what we're getting now with just sulcus to sulcus sizing. Okay, so what we did was to program all of these equations into a website, which is open and anybody can use it, and it's called ICLsizing.com. And the idea here was to base it on the ASCRS calculator. So if you have an OCT that's measuring anterior segment angle to angle, well, put those data in. If you have ultrasound, you can put that data in, and whatever you put in is what you get out. So for example, if you're putting in the lens power and the sulcus, you'll get the Doherty data. If you put in the anterior chamber depth, the sulcus, and the lens rise from the Kojima formula, it'll tell you use the 12.6. If you put in all the parameters, and that means you have ultrasound, then you'll get the 3.0 version where you'll get a prediction of the volt for each eye based on whatever lens you put in. And so you all know that the outcomes of the ICL are unbelievable, right? Because it's hard to believe that how accurate this machine is. The accuracy of ICL surgery equals pretty much the accuracy of your refraction. Because you're refracting, they see that, you order the lens, you put it in, well, they're going to see that, right? I mean, that's kind of obvious. So it is really an extraordinary technology. And of course, most of the eyes are, well, all of our eyes are within one line of their best spectacle corrected vision, uncorrected. The safety is superb, and the spherical equivalent attempted versus achieved is, as you'd expect, pretty crazy, 100% within a diopter, 83% within a half, and the cylinder control is very, very, very good. The contrast sensitivity, of course, is superb with this procedure. So in terms of its clinical outcomes, it's second to none. The question is the safety, and the safety is about the outliers, and the outliers are about the sizing. And so this is why I'm so excited about this, because I think that in a sense, this makes the ICL almost a bulletproof technology in terms of effectiveness and safety. Now, let's remember a couple of things which have cropped up over the years in listening to the real experts in this field. So Saldivar talks about predicting, or rather setting, the lens volt based on parameters. Now, remember that a high myopic lens, you might be thinking about what lens separation you want here, but remember that the high myopic lenses are thicker in the mid-periphery. That's how it works. So actually, the lens separation that you're interested in looking at is here. One of the reasons why in a high myopic eye, you're going to want a higher central lens separation than in a low myopic eye for the same actual separation between the crystalline lens and the ICL in the mid-periphery. And this image supports the notion that post-operative monitoring of the ICL, where is this lens now at 3 months, and where is it a year later, and where is it every 2 years after that, because they're coming back for their endothelial cell counts, and they're also coming back for high-frequency ultrasound scanning to make sure that the lens is in the right place and nothing's moved. So this introduces new graphs. So you're literally the first people that have ever seen these graphs, because we just plotted them. Never before have you seen a graph of attempted versus achieved lens separation, because no one's ever attempted a specific lens separation and then seen what lens separation they got and plotted it on a graph. So this is intended lens separation versus achieved. And as you can see, it's pretty good, not too bad. Obviously, most of our eyes are crowded around the 5 to 800 range, because that's what we've wanted them to be, because they're young myopes. And this is an accuracy of intended volt. So you can see we have 56% of the eyes within 100 microns of intended, and 90%, over 90% within 300 microns of intended volt. This is amazing, okay? To actually be able to prescribe the volt rather than see what you got from a recommended size. And when we go back to this graph and now see what we did achieve using the 3.0 formula now, since then, the interquartile range has now gone, as we predicted, to about half of what it was with our Kojima formula only. 250 microns with Kojima using sulcus to sulcus and lens rise, 163 micron interquartile distance. Very exciting. It makes this technology it makes me very, very comfortable, very confident about putting it in to young people who are going to grow for many, many years. So far, using the formula, our lowest that we achieved was 150 using the Kojima, and now the lowest is 270. So as you can see, we've brought the outliers in, and it's all about the outliers, right? Because the exchange rate is low, but let's remember that the exchange of an ICL is because the lens is dangerous. That's why you exchanged it. That doesn't mean ideal ICL, right? Because there are many ICLs that we leave in because of the relative risk of taking it out and putting another one in, even though the volt is not exactly where we would like it to be. It's a little bit lower, it's a little bit too high, but I'm not going to exchange it. Let's just monitor this patient. We're talking about the exchange rate being because of critical sizing problems. Those are the ones that will submit a patient to an extra surgery.